Thursday, yesterday night. So I'm sort of still on California time.
Okay.
So I have to refresh my memory where we were. So let's see, where were we? So we were talking about software reliability growth models. And I see the parameters. So this is what we were doing last time. We talked about the operational profile. Which represents the mix during actual operation. I was in ISRI, which is the International Symposium on Software Reliability Engineering. So during several presentations, people talked about operational profile. We did some work on operation profile a while ago, and we have shown that if you want to find faults fast, then operational profile is not the optimal way of testing, because it is good if you have limited testing time, but for high reliability, testing should probably be more random or more directed compared with operational profile. And I was mentioning about the exponential SRTM. Software reliability growth model. And I was mentioning about the model, and the model can be, it's usually stated this way. So this is the cumulative number of faults that would be found by time t, and this is the failure intensity. And I was mentioning, so this is the failure intensity. And if you would make plots of these, here's a plot for mu. So, and this is time. So as time passes by, the cumulative number of defects found would asymptotically approach beta 1.
Is that beta 1 or beta 0?
Oh, I'm sorry. You're right. That should be beta 0. So beta 0 represents, so we were talking about the parameters. So beta 0 is, we can say, initial number of faults. That are present in the software, and hence the eventual number of faults that would be fine if you will keep on testing forever. In actual practice, you will probably find a few more, because some of the false removed would be removed incorrectly. In other words, in the process you are going to inject a few new false. So the total number of faults you will eventually find would be slightly more than beta 0, perhaps 5% or so. And then I was mentioning about beta 1. So we're discussing this. And it is given by K divided by TL. And K is supposed to be a constant. It's fault exposure ratio, we were talking about it last time. And TL is the linear execution time. So TL is the time it will take if you will execute each instruction only once. So that is where you take the total number of source lines multiplied by the number of object instructions per source line. And this actually, Q would be different for different high-level languages and for different target processors. So for example, for a RISC processor, there are going to be more object instructions, and a CISC processor will probably take fewer instructions for the same high-level code. And the time it takes to execute one single instruction, so 1 by R is the number of instructions executed per second. So this is instruction execution rate for the processor. Now this assumes that you are measuring time in CPU time, execution time. If your time is measured more in terms of calendar time or man hours, then you need to appropriately do some conversion. So notice, this has an interpretation and this has an interpretation. And this is where we were last time.
Is R going to be in million operations per second or million instructions per second?
That is true. So R would be equal to number of instructions, number of object instructions per second. So this is referred to sometimes as the MIPS rating or whatever. The number of instructions, object instructions executed per second. And, oh, I think there's an assignment you guys are working on, right? And also a quiz. I think the quiz is already done, right?
I don't know.
Quiz, when is the quiz?
You didn't have a deadline mentioned on it.
Or the quiz did,
Yeah, I don't think I had a deadline.
quiz didn't have a deadline? Are you sure? Because the quiz, I guess it has to have a deadline.
It said unlimited on it.
Yeah. But you said, I think last week, you said both of.
Oh, I must have, oh, I see. Oh, so I forgot to put the deadline on it?
Yeah.
Yeah.
Oh, I said, you should have guessed my mind. So, okay, so I'll put some deadline. So let's make a deadline. What is the homework due?
Tomorrow night.
Tomorrow night? Okay, I guess the quiz was supposed to be due earlier. So the idea was that you would do the quiz first and then do the homework. Even though some of the, there's basically one is supposed to prepare you for the other. So, but it probably doesn't matter in which sequence you do it as long as you do it. So we'll make a deadline for the quiz, let's say, today's Thursday, right? So just make the deadline Thursday, Friday. Let's make it Saturday. So we have the quiz deadline Saturday. Okay, so this is where we were last time, and okay, so let us then continue from there. So one advantage of this model is that the parameters, they have a significance. Now there are other models that people have proposed, and there are quite a few. There's several dozen models. There are some that are, you will find often discussed in books or compared. We did a comparison of some of the popular models. But let me mention one other model that has been found to work well, and it is called the logarithmic Poisson model. Logarithmic Poisson model. And it also goes by the name of the people who came up with it, Musa Okimoto. Musa in his book calls it the logarithmic Poisson model. So we'll refer to it as the logarithmic model. And it has been found to have good predictive capability. And the model is specified in this way. So compare the equations. Okay, the logarithmic model or the Musa-Okimoto model, and this is the exponential model. It goes by various names, as I was mentioning. This is the most popular model. This is also fairly common, and this has been found to work best in many cases. Now notice that this is applicable as long as total number of faults found is less than or equal to the number of faults you have. In other words, once you have found all the faults, then the model no longer applies. So if you assume that you will keep on finding faults, then you will find infinite number of faults in this, as opposed to the exponential model, which is a finite faults model. So basically in the exponential model, in infinite time, you will find a finite number of faults. For Musa-Okimoto model, for infinite time, if you will not have this exclusion, you will find infinite number of faults. However, if you stop at when you have found all the faults, okay, you don't have to worry about reaching this condition, because in all real situations you will never find all the faults. So you don't have to worry about how do I find out that I have found all the faults, because you will never find all of them. So, but it is applicable as long as this condition is satisfied. So basically, this is a finite time model. It says, the model effectively says, the way I interpret it, it says that you can find all the faults in finite amount of time. It would be a long time, and it would be a time that would usually not be feasible for most real situations. It would be too long, but it will still be finite. And Now, what about the parameters, these two parameters, in this case, beta 0, beta 1, don't have a simple interpretation.